Okay, let's continue where we left off. So I'm going to jump straight to the weak form, put in the weak form equation. So this is what you'll see by default. This needs to be modified for your stress. This is linear momentum in the x direction. So when you work out that weak form, you're going to get an equation like that. And here, don't need that. We have this term and sxy. So that's it for the weak form. While we're here, let's go ahead and put in boundary conditions. So click on this, then right click, and I want to put in, I believe, a Dirichlet boundary on the top. Click that top, make sure you add it. No constraint in one, but here I'm going to put, what do I want to call this? Displacement y. Let's see. No, let's call it u2 naught. So I'm going to multiply this times t. I want it to be a linear function as long as t is less than, let's say, 1. Yeah, and then, and also, if t is less than 1, yeah, and let's say plus u2 naught times t greater than or equal to 1. Alright, so what this means is this displacement is going to start at 0. It's going to go all the way up to u2 naught when t equals 1. Then that's going to shut off the first term. And then it's going to be a constant after that. So these greater than, equal, or less than. Sorry, I don't know where that annoying ring's coming from. Coming back, this is the ramp, okay, and this will hold it constant. It'll be constant as long as t is greater than 1, and between 0 and 1 it's ramping up to that constant. So we're going to run a simulation from t equals 0 to 2 and see how that works out. Alright, we need another boundary condition. Click back, right click here. No. Right click, and we want a Dirichlet boundary 2, and I want this. So a roller means that we're going to fix this in the y, no constraint in the x. So add that one, and we need a roller on the other side. So let's add that one, and we're just constraining it in the x. Okay, so this is defined as a roller on that boundary. Right. Okay, now we need to go back, add some definitions. So right click on definitions. I think that automatically come up, but what I did is I quickly clicked on variables. So bring up variables, we need to define those stresses. Sxx will be C11 times EXX minus EXXP plus C12 times EYY minus EYYP. So the P's are the plastic strain. This will be C66 times EXY minus EXYP, and YY C12 times EXX minus EXP plus C11 EYY minus EYYP. Okay, so clearly there's things here we have to define. Let's first do the total strain. So that's U1X, EYY, U2Y. And I'm going through this fairly fast. There's another mechanics module that goes through this in more detail. I recommend looking at it if you get confused. U2X for my shear. Right now we're going to say this is purely linear elastic. So I'm just going to set all my plastic strains to 0 to start with. Almost done. Let's come up to variables. Okay. We need values for C11. This can be related to elastic modulus, Poisson ratio. And if I pull that out of the text, see if I can find that in Ready very quickly. Okay, so for plane strain, C11 will be E times 1 minus nu squared divided by 1 plus nu divided by 1 minus nu minus 2 times nu squared. C12 E times nu divided by 1 minus nu minus 2 times nu squared. C66 is E divided by 2 divided by 1 plus nu. And I believe that's it. Now there's something back on variables I think I missed. I think we need factor 2 right there. So I look up, yeah, so if you look up the constitutive relation, 11.2.3b in Reddy's book, this is the correct version. Alright, so I think I'm going to stop it here. We'll solve it on the next video.